Hello everyone, my name is Carlos Rivera and I am presenting the work Is this IoT device likely to be secure? A risk score prediction for IoT devices using gradient boosting machines. This work was done in collaboration with Arash Shaghaghi from RMIT University in Melbourne, Australia, David Nguyen and Salil Kanhere from the University of New South Wales in Sydney, Australia. Machines have come to replace humans in many activities, and according to the title of this note from DevOps.com, currently IoT devices have replaced people on being the weakest link in terms of security. This becomes a problem in enterprises where IoT devices are implemented in a bigger scale. In this type of organizations, not only automation is brought, but also vulnerabilities which later becomes point of an attack. Internet of Things, or IoT, facilitate advancements and financial benefits for organizations, and continue to transform and impact organizational processes and structures. IoT devices expand the plethora of attacks already aimed at organizations. These devices present unique challenges that cannot be adequately managed using conventional approaches. Traditional security mechanisms and risk assessment frameworks deployed in organizations fall short when it comes to IoT devices. Typically, IoT devices are produced by manufacturers and sold as is. The lack of standards and legal frameworks leave the security of devices as an option to manufacturers who are predominantly focused on issues such as cost, size, usability, and time to market. Vulnerability assessment of IoT devices is also costly for enterprises, given the exponential growth in numbers, variety, and configurations. Ongoing advancements in IoT devices limit the support period by manufacturers providing security patches. As a result of all this, IoT devices become orphans much earlier than traditional computing devices. Nonetheless, these vulnerable IoT devices have been reported to remain connected and vulnerable, leading to massive global security threats. Specialized news portals or technology organizations confirm that vulnerabilities such as the lack of security hardening mechanisms are present in the IoT devices even after being released to the market. Hackers regularly exploit IoT devices and compromise them. The best example of exploitation is the case of Mirai malware that in 2016 scanned segments of the internet and compromised around 380,000 IoT devices, as seen in figure 2 in the bottom. This paper hence provides a risk score prediction solution for enterprises, allowing system administrators to carry out an easy and cost-efficient risk prediction based on an IoT device's publicly available information. The approaches used to assess the security of IoT devices are similar to those applied in computer systems. For instance, the security testing approach has several options such as discovery analysis, vulnerability assessment, security assessment, penetration testing, and security audit. However, all these require a certain level of interaction with the assessed device. Risk assessment approach, on the other hand, is more like a process that analyzes the devices looking for vulnerabilities. Then a risk score of the vulnerability found is calculated and associated to the device. There are many proposals to carry the risk assessment to technological devices. One of the most used is the CVSS, or Common Vulnerability Scoring System, from the National Institute of Standards and Technology in the US, or simply NIST. In our work, we utilize machine learning algorithms to predict CVSS risk score. In the literature, we can find previous efforts where automatic analysis and classification of vulnerability databases has been the subject of prior research. For instance, Stefan Neuhaus and Thomas Zimmerman proposed to analyze the entire common vulnerabilities and exposures of our CVE database to classify the vulnerabilities by topic. Their approach focuses on analyzing the whole database and aiming to find tendencies over the main topics. Yuan Wang and Min-Se Huo proposed to categorize vulnerabilities using Bayesian networks. These authors aim to predict the category of software security vulnerabilities, also through the analysis of the CVE database. Sarang Na et al. Proposed to classify vulnerabilities from the CVE database. This, however, is based on a Bayes algorithm. Here, the authors aim to predict the type of weakness of each vulnerability. To the best of our knowledge, risk prediction for IoT devices using their publicly accessible features is novel in the related literature. We believe the solution proposed by Gregors et al. Is the closest work to ours. In this work, authors aim to predict the category of a vulnerable IoT device. For this, they propose a classification of device-related vulnerability data for IoT and industrial IoT equipment. Authors divided CVE records into 7 categories, then used the support vector machine classifier on the device and vulnerability data to predict new categories of vulnerabilities. To narrow the data universe, they opted only to obtain data flagged with the value hardware. In our proposal, however, we combine features from the National Vulnerability Database with publicly accessible information about devices to create new balanced dataset. In this case, just about vulnerable IoT devices. We notice data imbalance based on information available in the model used in Gregor's proposal. Here, their model struggled to differentiate some of the classes. In our solution, we perform several processes to our dataset to determine the level of imbalance, which was later leveraged over the model. In the proposal of Gregors et al., they perform analysis over models rather than over the data, whereas in our implementation, we analyze the data thoroughly to identify the adequate machine learning model. Also, in Gregors et al., it was used the data from specific years for the datasets, for example, 2015 as training data and the year 2016 as test data. In our model, however, it contains records from the year 2013 to 2021, here up to the 17th of June, of course. And we split the data using the whole dataset rather than per year. Although Gregors et al. Aim to predict the category of vulnerable IoT and industrial IoT devices, they use the entire dataset, which contains information related to other types of systems. Since the National Vulnerability Database contains poor references to their target type of devices, in our proposal we narrow the analysis to only IoT devices, and we ensure that all of the other features were directly related to the target devices. As a result, we created a unique IoT vulnerability dataset with information about each device that could be reused in future research. We studied the vulnerabilities from the National Vulnerability Database, focusing on only IoT devices. We analyzed 1,153 records, this from the past 8 years, taking as a starting point the year 2021 and went back. We aim to extract information related to the affected device. However, we realized the detail and quality of information in each record is different. Because of this, we use only the information that is constant and most probable to appear on every record. For instance, the CVE identifier, the severity, and the affected device name. The references that come with the CVE record were used to confirm the product name and manufacturer's information. We disregarded the weakness information because this value is not related to the device but to the vulnerability. Regarding the CPE information or common platform enumeration, was also discarded because the information that is provided through this system or format is also incomplete. For the rest of the information in our dataset, we use Internet and gather information related to the affected products. We focus especially on getting device specifications such as the protocols used and common configurations, retail information such as the price and release date, and from corporate sites information like the name of the company that manufactured the product and the device's user's manual. In the analysis process, we initially proposed gathering information related to 27 features, this for a sample of 300 devices. We constantly reduced the number of features and discarded those that were not possible to collect for the 100% of the sample. After several trials, we completed the 100% for only 11 features. Here, an extract of the dataset. The first column contains the CVE ID, We kept this for control and identification purposes, but never used in the machine learning process. The feature brand, product type, category, price in US dollars, protocols, data storage for the location of the data used by the device, personal information or personal info to keep the track if the device uses personal information, location to keep track for the devices that have this feature enabled, auto encryption to record if the device has any encryption mechanism at the authorization service, communication cap or communication capability to represent all the communication services or capabilities of the device, and lastly the label that we predicted with the machine learning models as the CVSS score or the Common Vulnerability Scoring System score. The National Vulnerability Database has a metric system to measure the severity of vulnerabilities. Currently they have two versions. Version 2 that has 3 classes, while version 3 that has 4 classes, which is more descriptive. We use then version 3 as the classes to predict. Once we define the severity to use as label and the features to gather data, we aim to obtain the information of at least 1000 records. When we reached this number, we analyzed the data and found a huge imbalance. The data was distributed initially as 10% for low class, 7% for medium class, 18% for high class, and 65% for critical class. Because of this imbalance, we decided to obtain more records from the classes low and medium, perhaps looking to reach the same percentage as the class high. In the end, we could reach a close percentage between the classes low and high. And while the class medium is not at the same percentage of the other classes, we could level it up to 12%. And while the percentage for the class critical got to 57%. In the end, we reached 1,153 records and managed to reduce the imbalance. From here, we use other methods to manage the remaining imbalance in the data. We utilize several techniques to transform the data into values that could be used by the machine learning models. Firstly, we use level encoding to convert text into numbers. Then, through text frequency, we generated counts per each feature. And because of the data had different maximum values, especially features such as the price, we applied the standard function to scale the data. Note that this specific process can be applied to all the data or per feature. In our case, it was applied per feature as the data has no link between features. The result was an increase in the performance of the machine learning models, as we will see ahead. At this stage, the data can be submitted to the machine learning models. However, we wanted to validate that the existing methods to reduce dimensionality are of use and perhaps increase the performance results of the machine learning models. For this, we selected the techniques TSNE or T-distributed stochastic neighborhood embedding and PCA or principal component analysis. The former generates clusters of data based on the distance between points or data records. The latter reduces the dimensions of the dataset from n to a number that best fits the model without losing data. In our case, the ideal number of dimensions was 3. For this, we carried 3 trials, one where the data has no dimensionality reduction. This can be seen in the figure as WO/DR or without dimensionality reduction. The second trial has TSNE applied and the label in the figure is W/TSNE, and in the third it has PCA applied and it is represented in the figure as W/PCA. The numbers shown correspond to the evaluation metrics precision, recall, and F1 score. Each column has the corresponding value for each metric, and because this is a multi-level problem, we have results for each level: low, medium, high, and critical. The value macro corresponds to calculation of the overall mean of the metric, and the micro column corresponds to the average of all samples without using class weights. Note that this value is the same as the accuracy. For better appreciation, the numbers above or equal to 70% are in bold. In the graph, we can see that the results from not applying a dimensionality reduction are better. In terms of machine learning models, we evaluated ensemble models as we found them appropriate and suitable for our multi-level problem. Note this type of model works in individual format or in an aggregated format, which is our case as well. These models are designed to combine predictions from several built-in models or submodels that are arranged in a way that increases the prediction capability. Another of the advantages of this type of models is that they reduce the error and resolve bias problems, a feature not present in individual models. We tested the gradient boosting machines model, AdaBoost classification model, random forest classifier, extra tree classifier, and voting classifier. From these classifiers, almost all use decision trees as the base model, being the voting classifier the one that does not depend on this, but rather hosts any type of model. In prior trials, we found the models extra tree and AdaBoost classifier to provide the lowest evaluation results, so we discarded their use. Because of the limited size of our dataset as well, we decided to use the cross-validation technique to split the data and then use the classification models. Note that there are several methods to carry the cross-validation, and because of the imbalance of our dataset, we use the stratified repeated cross-validation. This method divides the data in a random manner, but balancing the number of classes in each segment. We tested several combinations and found that using 5 folds with 2 repeats was the best option. In the table showed, we compared the performance of the models gradient boosting machine, voting classifier, and random forest classifier. The level of the columns corresponds to the results from using the cross-validation execution. For example, R1, F1 corresponds to the wrong one of the fold 1, and the values shown correspond to the accuracy obtained. In the graph, the label run A corresponds to the results of the trial without applying any dimensionality reduction. Run B has applied TSNE and Run C has PCA applied. With this set of trials, we confirmed that the models perform better without any dimensionality reduction technique applied, and that amongst the models also confirmed that the gradient boosting model is better in comparison to the other ensemble models. The conclusion from this experiment is that the best classification model for our dataset and label to predict is the gradient boosting machine classifier. In this paper, we propose a novel approach that can predict the risk score in IoT devices. This solution can be considered complementary to current IoT threat detection and prevention mechanisms and risk management frameworks. With our proposed solution, enterprises could now perform an easy and cost-efficient analysis of their IoT devices and filter out those with high risk categories, or perhaps just high or medium risk categories. This is achieved by relying on the public accessible information of the devices. We created as a result the first balanced dataset of IoT devices with 1,153 records. This dataset was used to fit and train the gradient boosting decision tree or classifier machine learning model to predict the risk score for the IoT devices. This model achieved 71% in prediction accuracy. Also, we compared this model with other ensemble models and we proved that it was the best one. Also, it was not necessary to apply dimensionality reduction techniques to increase the performance of the prediction model. In the future, we plan to extend this analysis and use the dataset to provide more specific predictions and the type of vulnerability of devices, and also suggest the set of recommended actions to the system administrators to help protecting their networks. These are the sources of images and publications mentioned in the related literature. With this slide, I conclude the presentation. Thank you for watching.